How are you guys doing?
Good.
Good. All right. Yeah. Nice. It is a beautiful day. Maybe we're more awakened by this. I don't really have any business or anything, guys. Remember, if you're missing assignments, check your Moodle. Make sure you're not failing. Do your assignments. Send me any late videos so that I can score them for you. Uh, otherwise, any questions over anything like that? Good. Okay. Um. Let's review where we stopped off last week, and let me make sure I give you guys some participation points for being here and thinking about stuff. Uh, I've almost figured out most of your names, but probably should tell me your name anyways, just to be safe. Um, Thoughts, questions, what's up? Where did you guys walk away last week? What was on your mind? Or at least, what did we do? Let's figure out where we're at in this whole story of the solar system. Come on. You guys are afraid. I know somebody was awake. There must be some. Just throw something out there. What do you remember? Anything? Yeah. Isaac, right? All right.
Wasn't it last Tuesday we talked a lot about Kepler, right?
We did. Yeah. Who's Kepler?
He's
Why do we care about Kepler?
an early astronomer. I mean, he helped develop like the heliocentric model, right? And he was Tycho is it Brahe, his apprentice, and he's got like his three laws, or is it three? Yes, three. He's got like the first one about like orbits have to be elliptical, or like the orbits are elliptical, and
That was the main thing. Yeah.
then about orbital speed, I believe.
Yeah. Yes. Yeah. Yeah.
I don't remember what the third one was.
Yeah. It's all pretty crazy. He has some really wild revelations that he used to sort of adjust Copernicus's model. Remember, Copernicus had this. He still kept the perfect circles. Everybody believed in perfect circles for thousands of years. And so that wasn't working out. Kepler was examining the data and trying. He liked Copernicus's idea because he was getting sick of all of these weird adjustments getting tacked onto the Ptolemaic astronomers' worldview. The mathematical physics was getting too abstruse for him. And so he wanted to refine it, but he couldn't make the perfect circles work. So you're right. He had this idea, what if we just squish the circles a little bit? And that seemed to work out. So that's kind of why we remember him. He also, like you said, realized that in doing so, that meant that the planets were moving at different speeds at different parts of their orbits, which is pretty weird too. And then somebody came along next and made a little bit more sense of that. Yeah. Mm-hmm.
And he fixed that sort of not equation, but Kepler had a
Yeah, you got it.
what's the word? Oh my gosh.
Anybody?
He said
M-
that the
Dr. DeLay's favorite math symbol. It's
yes.
proportional. Yeah,
Newton made it
proportions.
equal when he factored in the mass of both objects that were orbiting each other.
Yeah. Yeah, it's really cool. So I think that one of the first things, if as a scientist or as a person, you're going out there, you're kind of making patterns. If you're seeing things happening, this will happen to all of you guys, even though you're not going to become scientists, but you're going to see things in the world that nobody's ever seen. And the first thing you see is just that there's some relationship between two variables, right? That's really what it comes down to. Like, oh, like French fries make me sick. I don't know, anything, whatever it is, right? And then you kind of learn how to scale that and you figure out, oh, wait, it's just this one type of French fry, or it's if I eat too many French fries, or it's if they're fried in coconut oil instead of whatever I like, like, so you're always tuning these. And so that's what Newton did. That's right. He thought, hey, I can actually make this proportionality sign go away. In other words, I can figure out why some planets go faster than others, regardless of their distance from the sun. I can figure that out if I assume that some planets are bigger than others, basically. And he used this word mass really ambiguously. And so I think, if I recall correctly, we closed down class last time wrestling with what the heck this concept of mass really means. Because there's some weird little bits of the story, and actually it gets weirder if we go even deeper into it. And I pointed out that all of the atoms seem to have different levels of mass. What does that actually mean? If you look at their size, like how wide their atomic radius is, it's not really in proportion to their mass exactly. There's some trending there, but it's a little bit more complicated. Dante, yeah.
I remember last time I started going into a bit of a rabbit hole.
Yeah.
Just thinking about mass, and this might
Yep.
be going a little ahead, but I found a quote from Einstein about how because most people don't understand what his equation E equals mc squared actually means.
Okay.
Basically, just
We're gonna get to it, I think. Yeah.
are the same thing. Right? His quote was, "It followed from the special theory of relativity that mass and energy are both but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind."
Yeah. We're gonna, man. Yeah, we're gonna get into that more because we have to deal with fusion, and that equation is really essential to fusion next semester. Yeah. So there is some sort of we don't really talk about energy much in this class. Um, and I feel deeply uncomfortable cracking open that can of worms without giving it its due diligence. But yeah, I think that there is something related to those three variables. You know, a speed, something heavy, some sort of mass, right? Some amount of material, and then the amount of energy that can be achieved as a result of that. That requires us to really think about what's it mean when you have a lot of energy. You know.
I brought it because that might be why Newton had used it so vaguely, because he might have had a vague understanding of a similar concept.
You know, it's still really vague is kind of the good and the bad news. So, you know, if we go, I could spend the rest of this class talking to you guys about the concept of mass because, you know, at this point, people don't even use the master kilogram for mass. They actually use a proportional amount of deflection from a magnet, so an equivalent form of mass. And this gets into really crazy territory because they start treating electric force as if it is mass in and of itself. So you find things like the electron having mass, which is really just their magnetic deflection equivalent in terms of the force being applied. So the concept of mass has not gotten clearer. It has actually gotten less clear in recent years. And there are people who, you know, this is their whole bread and butter, is trying to iron this out. But it's fun. I don't know. I think it'll keep coming up in some sense. I think for the purposes of talking about the planets, we can think of mass more or less as the amount of atoms that are there. I think it's a good, like, rough. It's not totally obvious. Again, it's not quite right, but it's close. It does reflect something about an atom's ability to stay put. That's the inertial side that Newton elaborated in his F equals ma business. It also tells us something about the atom's ability to be pulled on by each other, which is the gravitational side of things. Those turn out to be two sides of the same structural feature of the atoms at the end of the day, but that's kind of getting beyond the scope of this. Yeah.
Is it possible for a planet to fall out of orbit?
Yes. What's your name again? I forget.
Jared.
Jared?
Yeah.
Well, possibility. So this is a really fun line of questions. I really like this line of questions, but it becomes a statistical question. You know, there's a lot of people that will argue that there's a lot of questions that point towards similar explanations, which is like, why is it that when we look up at the other planets, why don't we see a lot of life forms and humans and beings everywhere? And then they extend that, and they're like, man, we're looking at other star systems, and we don't see a lot of signs of life in general. And the question becomes, why is that? And a lot of the arguments for that default to, well, we are a really, really rare system that's been subject to a lot of good luck over the years. And because of all of these circumstances, you know, we happen to have a planet that's of the right composition, that's in the right location, that it all just has provided this perfect stage for, you know, this scene in this room today to unfold. And the same argument could be applied to, you know, how likely is it for a planet to leave or come into the orbit? Well, it seems really, really unlikely, but certainly not impossible. Maybe it's happened in the past. You know, one of my favorite pieces of ancient history, one of my favorite mysteries of ancient history is this thing called Snowball Earth. Do you guys know about this? Pretty crazy. So the Earth, at some point in time, appears to have been covered in about, I don't know what it was, I don't know, now don't quote me on this, but I don't know, like 5 kilometers of ice or something. The whole thing, not just the North Pole, the South Pole. I mean, we have these periodic glaciations every, you know, this cycle that's like, let's say, 100,000 years long or something like this. But what happened in this period? This was several billions of years ago. And after this period, life changed completely. So we went from having these really basic life forms to these diverse, like photosynthetic life forms. Weird stuff happened after this. Something absolutely freaking crazy happened once, and one time only in the history of life on this planet. So what on earth would cause the Earth to freeze over with, 5 kilometers of ice? Well, I was talking to one of my astronomer friends, this guy, I think I mentioned him before, he does these simulations at the University of Bordeaux in France. And we were just kind of playing with ideas. And again, this is like the weird thing about talking about ancient history is that no one's ever going to know for sure. I could make a really compelling argument for you and I could be totally wrong. But we said, how long, let's say we just cut the Earth from its leash right now. So let's assume that all of Earth's atoms are somehow tethered to the sun through some mechanics that we frankly just don't have any consensus on at this point. Let's say we just cut that leash and it just flew off its handle. Well, the Earth's actually rolling pretty fast around the sun, so it would fly pretty fast. I don't have the numbers off the top of my head, but it's several thousands of kilometers per hour, right? And we did the calculation, and we're like, how long would it take for the Earth to just fly to the next star system? Assuming it was perfectly lined up, it was just a straight shot. And it's actually not that long. Something on the order of like 40, 50,000 years. So what happens if you take a planet that has some form of development like the early Earth, let's not even say early, but early life on Earth form. It has some oceans, some heat vents, some very primordial, very basic life. And you throw it off into space. Could it freeze over and survive and join another star system altogether? I mean, nobody on Earth, like no scientists in their right mind would say that that's a likely thing to have happened. But nobody has any idea why the snowball Earth happened either. So I don't know. These things get into all of these discussions of super ancient histories. They really force you to flex your imagination in some sense because for most of these things, either the extant explanations are insufficient, they have blaring contradictions that hurt your brain, or they just don't have explanations at all, right? And so, yeah, the possibility space has to be pretty wacky, but why shouldn't it be? Like, why should we expect that the history of our planet is some nice, clean story, right? If it was like that, we would probably see them all over the place and they would all sort of look homogeneously the same in various stages of development. But the planets are all really weird looking. There's lots of different types, they're different sizes, they're different they're different stages in some sort of evolution.
I think it would be good to go over. I just looked up the current theory for Snowball Earth,
Oh, yeah, what is that?
which is that the breakup of the supercontinent Rodinia
Mm,
combined with the preponderance of tropical continents may have increased silicate weathering, lowering CO2 levels in the atmosphere and triggering basically a runoff effect of global cooling, where the more ice and snow there was, the higher the albedo effect, i.e., the more sun and heat was reflected off of the Earth, and the less greenhouse gases there was to trap it in the atmosphere. And so you created a runoff effect of just global cooling until you had a snowball Earth, until eventually the inverse effect happened. And that inverse is what we don't, there was no explanation.
yeah. It may be so. It may be so. I have deep thoughts about Rodinia and stuff too, but we'll get to that when we get to the Earth. We're actually not at the Earth yet, believe it or not. We're going to go to Mercury. Yeah, bummer. Well, yeah, that's more. Yeah, that's true. That's a good point. The way the textbook is designed is that we'll treat Earth as a geological object soon, and we will talk about such things as plate tectonics and Rodinia and all of this. Um, Yeah, it may be so. That's I prefer a world. I prefer to live in a world where we can. I really appreciate you pointing that out, and I think that we should really saturate our mind with possible theories, especially for these ancient history things, because um, it's very difficult to put any certainty on these, regardless of how strongly we can construct these arguments. We're never going to get to go back and see it. That's for sure. It's tricky.
Never said never.
Never say never. Yeah, maybe you'll build the first time machine. We'll talk about time today, though. and then maybe I'll disavow you of that notion. All right. What else, guys? Anything? That kind of brought us up to speed, I guess, for the most part. Yeah.
For this week. But like
You guys are a bit ahead of me in the reading, I think. But yeah, I'll take the question. Yeah.
telescopes and
Yeah.
them, like if I'm not mistaken, like a lot of it is like using mirrors. Um I can't wrap my brain around like how we would advance them, but I've like I don't know how to word this. Um, do you think there's like a cap on how far we'll be able to advance them and like how far we'll be able to see, or do you just think we'll just like keep
I wouldn't bet on it, but I also wonder if when light is so I kind of see what happens when light comes from the sun to us is that it doesn't just come directly from the sun to your eyeball. It's relayed through a number of atoms along the way. Some of them relay it pristinely, some of them scatter it, but at the end of the day, there's a massive like I think about light, gravity, all of these things as network effects. And I imagine that when light has to travel for 15 billion light years, maybe 20 billion, I mean, the universe isn't even supposed to have 20 billion light years, but maybe they'll build a bigger telescope and it'll have 20 billions of light years. I imagine that at some point, you accumulate so many relays that things get weird. It's like, have you guys ever seen those tests where they compress a JPEG like 5,000 times in a row and it just turns into garbage at some point? I'm a little bit afraid that when we're interpreting these really long distance redshifts and weird looking bright objects and stuff, that we're looking at a little bit of compression due to the relay space that's undergone already. So in some sense, I'm like, maybe we'll be able to keep seeing further, more sensitive, but it might be kind of messed up. And people might not realize that at first, and they might make up some crazy conclusions. That might already be happening. So I don't know. That's a good question. I like that. It's a good question. Yeah.
Just kind of building on that. I mean, right now, the only way that we interact and perceive the universe is through the electromagnetic spectrum.
That's right.
Visible light or infrared. Or,
Mostly, yeah, for the most part.
and that interaction and perception of the universe might have a limit telescopically or however we manage to create those technologies to perceive it. But by the time we reach that limit, there may be other mediums through which we can perceive further or different things or different aspects. We're kind of looking at the universe through only one lens. And
We never know what we don't know. That's kind of one of the weirdest pieces of any puzzle, right?
yeah,
It's like you just if there's something that has yet to be discovered fundamentally about nature, right? Like you got to think. I mean, there was a point in time where people didn't know about electricity, like, and it wasn't that long ago, right? So you might have some experience where you experience static electricity or something, but it wasn't part of this scientific wheelhouse for how people apprehended nature. And now it's completely central, right? I mean, it's still very vague and there's problems, but yeah, if there are other phenomena that we can measure in the future that we don't even know to look for right now. Yeah. And that's part of the kind of humility about all of this. It's like, yo, these are our theories. We're doing the best we can. A theory, a model, it's like a model airplane. Like it's definitionally missing some elements of the real thing. Otherwise, you'd just call it an airplane, right? So all these models are simplified in some sense. They're all imperfect. Most of them will be updated with better versions of themselves as the years wear on. And that's the cool part. Like that's the practice. That's the art. That's kind of really that's why this is something worth preserving into the future. We can get rid of bad ideas without getting rid of the process itself. All right. Shall we keep going? Any further thoughts about last week? Oh, Andrew did mention this entropic gravity, which my wife, when I got home, reminded me that we actually interviewed a guy about entropic gravity, but it made no freaking sense to me at the time, and I blacked it out of my memory. But the basic, I started thinking about it a little bit more, and I think the basic idea there was that something like you guys know about entropy at all? Let's maybe start there. So entropy is this idea that, given all things being equal, any physical system is going to tend towards disorder, right? I mean, you probably experienced this to some extent. Maybe your rooms kind of do this, right? If you don't actually clean your house, it'll just turn into madness. So you have to apply energy to keep things ordered, essentially. And so, this seems to be a generalizable principle of the universe. I'm not sure how much it plays out on huge cosmic structural scales. The most popular idea right now is that the universe is going to end in this heat death thing, which is an entropic death because, of course, if everything just goes to sort of this random hiss and just sort of spreads out and fades away, there will be no structures at all. There will be no planets, suns, people, nothing. And that's the highest entropic version in some sense. The idea is that that plays out on the local scales as well, that things are tending towards disorder, but kind of in order to pay for that, you have to have local areas of order, which at a fundamental atomic scale turns out to be this gravitational process that results from it. Which isn't like too far in conflict with the way I think about it. I just think about still needing some sort of structural mechanical way to that this accounting balance is paid for. So this is kind of where I was going with the structure of the atom at the end of class last time. So that was it. That was interesting. Yeah. It was. I guess it was developed by this guy Eric Verlinde back in 2010. Gosh, I can't even remember the dude we talked to. It was a much later guy who was working on some elements of this.
Was it a film podcast or reported?
Mm-hmm. Yeah. I can send it to you, or I can throw it in Moodle for you guys too if you want to check it out. Yeah, I have a hard time sometimes with these. So it's a very abstract approach to a physical phenomenon, right? And I told you guys at the beginning of this that I think there's a lot of madness that results from like not grounding physical explanations in physical actors. And so I was probably losing my mind during this podcast about that at the time. It's kind of what I tend to do. But yeah, I don't know. We get places. It's okay. All right. So I think we can keep rolling with this. We talked about Newton's laws. We talked about this. Maybe to circle back. Remind me your name one more time. Jared. Yeah. What Jared was talking about is, can the planets like leave their orbits? It really is a balance between these two opposing, for lack of a better word, forces. But we could just say motions too, right? There's some sort of tethering of the planets to each other and to the great largest object in the solar system, which we believe is the sun. And there's also the fact that they're flying around at breakneck speed around the sun. So there's a lot of, there's this tendency for them to want to just fly off the leash, like I said. However, they're all in these perfect balances of this inward tendency, the pull of gravity, versus that tendency, that forward motion, which would just take them sailing off into the distance. And they are in this miraculously perfect balance. If they went faster, they would fly off the leash. If they went slower, they would spiral into the sun. It's kind of bananas. So this is kind of where I sympathize with these people who say, well, this is just a super rare system. There might have been gazillions of other star systems where the Earth-like planets flew off the leash and ended up in interstellar space and turned into, icy moons or something. And there might be systems where they just get gobbled up by their stars, and that's that. They might have been part of stars that didn't live that long, or their binaries swept them into oblivion. So yeah, this kind of balance is actually quite profound. It's worth keeping in mind. All right, so that takes us up to a new section on this. We made it through orbits, we made it through gravitation. Today, I want to dig into a couple of points about how astronomers measure the sky, and it's a little bit tedious, but they're really confusing, and I wanted to point them out. We need to talk a little bit more about seasons as they affect our observations here, and then time itself, which is always kind of a fun subject because everybody always has really far-out ideas about what time is. Before we get to that, though, I did want to mention the last piece of the puzzle with respect to the heliocentric versus geocentric model. You might think, okay, Copernicus, Galileo, Kepler, it's over, right? And you got to keep in mind Newton, too. Newton, right? We can't leave Newton out. Newton published that piece around the turn of the 1700s, that century. So what's that, the 18th century. Newton published that piece. This debate wasn't settled until Foucault built this pendulum in 1851. This was the first real experimental proof that the Earth was rotating. And I think it's worth mentioning because it's kind of a cool experiment. Have you guys ever seen one of these giant pendulums before at like a science museum or anything like that? They're kind of cool, right? I used to work at a science museum when I was a little kid. They had a huge one of these things, very much like that. And this is a pretty cool experiment. I think it's worth just pointing out because it's, again, I love these really simple ideas that kind of lock down far out ideas. Now, by the time Foucault came around, I mean, this, like I said, these other guys had made a pretty good case, but the case was somewhat circumstantial still. It was like, well, it would simplify things if the Earth was not at the center of the universe, if the sun was instead. That would be simpler. That was kind of the extent of their argument, really. And Galileo, he pointed his telescope and was like, well, not only would it be simpler, but it would be more in line with these kind of other orbital systems we see. That Jupiter thing over there seems to have stuff orbiting it too. That might be what's going on here, right? But that's a bit circumstantial, right? If this is a court case, it's kind of hearsay in a way. It's not directly testing the principle on Earth here in a laboratory. So what Foucault did was he realized that if you take like a pendulum, I could probably do this with my car keys. So if you take a pendulum and you just swing it back and forth, it'll have some predictable period that really is just a product of its mass and a few other, really just its mass. It's going to have a very predictable period to it, how long it takes to go like this. I hope I don't hypnotize you guys doing this. And then Foucault realized that, hey, if this is actually on a spinning surface, the globe is actually spinning, that not only will the pendulum go back and forth, but it should be precessing a little bit, right? If I move my hand like this, you can see the pendulum starts to actually spin in this way as well. It's like a really, really simple idea. He's like, I'm going to build a big one of these, and I expect that the Earth, if it really is spinning, it's going to get this pendulum going in the other axis as well. And he did it, and it worked. And I think that was actually the absolute death knell for the geocentric universe people. So, okay, I just want to tell you guys that story because it's really funny that it took that to really close down this argument. I think that's kind of cool. So this was a scientific debate that spanned. When did we start this story? When were these guys? Almost 300 years, it seems like people were split over this. It's a really long time to be on the fence about stuff. But I'm sure there's things like that we'll find ourselves waking up to in the coming centuries. All right, we need to talk a tiny bit about the way that the Earth is divided up to, not the Earth, the sky a little bit more. There's a couple of confusing concepts that might pop up in the story ahead, and we should be sure to make sense of them. So we talked about how the North Star was really nice for finding your latitude, right? That's really easy. You can do it at home. If you can basically measure a degree with your pinky, you kind of know how many degrees you are above the horizon if you can find the North Star, which is nice. You know where you are on the northern or southern hemisphere. Figuring out longitude, which is how far you are east or west, turns out to be a lot trickier, although it was super important to the early navigators, right? Because they're especially people crossing the Atlantic or the Pacific or something like that. Well, how do you know where you are? You're just in the ocean for days and days and days. How do you know how far you've gone, right? So figuring out this longitude thing turns out to be actually quite tricky, and it requires you essentially, well, how would you do it? Maybe you guys already read about this, but how do you think that you would figure out your longitude? If you had to, if you're on a ship, how do you know how far you are, east or west? That's a hard question. What's that?
I forgot.
You forgot. Maybe you can derive it from first principles. Yeah.
Based off of the other constellations or something.
That's a little bit tricky because it might be cloudy. But yes, so people do get by with a little bit of, they also have catalogs of where the moon should be on any given year, and so they can kind of be like, well, the moon should be over here, we're over here, so maybe we're not quite that far. There's some of that works, but it's a nightmare if the sky is cloudy, which it often is when you're at sea. Yeah.
Just a random guess, but could it be where the sun's gone?
Yeah, so this again, the sun also moves eastward by, I forget what it is, like a quarter of a degree a day or something like that. So again, just like with the moon, you could use like some what do they call these things, almanacs, to try to piece this together. Um, but the clouds, if you guys, anybody ever been to San Francisco before in the summer? You can't tell where the sun is. It's so dark. I lived there for many years. Yeah.
Is it based on timing how long the day is?
Well, it is based on timing. So it could be based on timing length of the day, but timing in general was a nightmare. Think about it. How do you like? We all take it for granted. I mean, we got these little computers in our pocket that tell us the time. Before that, people had the wind-up watches. Those are all really, clocks are really, like these precision clocks are a completely modern invention. Um, so it really came down to timing. That's really what it comes down to, because if you can count, if you can tell how fast you're going, they have ways of doing that. Basically, they'd have like a big pile of rope. They'd tie knots in it at a periodic length and then throw the rope out of the side of the boat and see how many knots get pulled out of the bucket per unit time. So you have to have a really precise measure of time in order to know how fast you're going. If you know how fast you're going, then you can say how far you've gone east or west. Presumably somebody's kind of keeping track of which direction you're headed and stuff. And you can actually kind of gauge longitudinally how far you are on the map. But yeah, it requires time. And so that's been a really interesting challenge across the years, is developing clocks that help you make sense of that. So we have to kind of do something similar. Now, we have to do something similar in astronomy, which is find, a starting place. By the way, this is when we say the 0 point for longitude, it makes sense with the equator, right? The 0 point would be right on the equator, because, well, at 90 degrees either way, you could have the celestial north and south poles. With longitude, where do you think they put the 0 degree? Yeah.
It's a Greenwich.
Yeah. Why is it in Greenwich?
Because the guy who made it was in there.
Yeah, that's the Royal Empire was on top of the world at the time, right? They were the big dogs on the imperial sea. They were doing all the astronomy. So yeah, they said it's going to be here in England at our observatory. Yeah. Yeah, huge navy at the time. Yeah, absolutely. Okay, so the 0 degree point has no astronomical relevance whatsoever for longitude. It is just where the guys who were in charge decided to put it. That's all there is to it. Okay, so we have to do something a little bit weirder, and this is the one thing I wanted to review with you guys, because this is super confusing, and I don't know, maybe you don't care that much. I won't spend too much time on it, but I think it's worth pointing out if you ever hear this stuff. We have to divide up the sky according to a system of longitude and latitude as well. And that's a little trickier in some sense, because we have that celestial sphere over our head, right? So we have to figure out how to make these 0 points, and it's a little bit bizarre how we do that. So in terms of the up and down pieces, the latitude, that's a little bit easier to ascribe. We basically just say from the celestial equator, right? We're just going to count degrees over our head. By the way, I think it's worth making an aside. What's up with degrees? It's a pretty weird system, right, of dividing things up. We do everything else in decimal points, right? But we do degrees in units of 60. You guys ever thought about that before? Pretty bizarre, right? Yeah?
Because you're tracking distance over a sphere, so you're dealing with an arc.
Why do you divide the sphere into 360 degrees, though? So weird.
Just because it nicely divides by 3, 12.
You could divide a sphere into 10 or whatever you wanted.
We're dealing with time, right? It's time.
Yeah, why did they do that, though? Why units of 60? Why units of 60? Does anybody know?
Dominant system of time.
When? When?
60.
Who? Yeah, it was the Sumerians. That's right. This stuff is like 5,000 years old. We started doing this. Started dividing circles up into 360 degrees, and we still do it. It's completely bananas, because the Sumerians counted everything in units of 60s. Like if you wanted like to pay for vegetables or something, you'd probably pay with a $60 bill or something. Like everything was units of 60s. We do units of 10s here and everything else, but for some strange reason, we have stuck with the Sumerian Babylonian tradition of dividing up circles into 60s and divisions thereof. So we have this degrees, minutes, seconds, arc seconds business that we divide things up. Anyways, so back to our celestial sphere, our sky. And this is the way that generally, these are the kind of coordinate systems that you'll use if you ever look at a star catalog or something, if you guys get one of those programmable. Does anybody have a programmable telescope? No, I don't either. They're very fancy. I have like a regular old telescope. You gotta twist it. So I don't use this stuff. But if you did want to use one of those, you would program in the coordinates of the location. And you would use this really bizarre system of right ascension and declination. So declination makes sense. It's basically, that one's easy to comprehend. It's basically just your elevation above the celestial equator. The right ascension is pretty bizarre. So again, for the longitudinal system, in other words, like where you are east to west, they had no obvious 0 points. So what happens when you look at the celestial sphere is that as the year progresses, the sun appears, and really all the planets, appear to trace out a path of the ecliptic around the celestial sphere. It moves a little bit eastward in the celestial sphere every day, but in reality, you're actually moving. But from the perspective of the celestial sphere, it's moving overhead. At some point, it's going to cross northward the celestial equator. That actually happens on the spring equinox. So what they do is they set the 0 point for their longitude system, right ascension, as the place on the celestial equator where the sun crosses its path on the spring equinox. Really bizarre. So I just wanted to point that out because it took me forever to understand what the heck they were on about with this right ascension stuff. Yeah.
I'm guessing I'm probably not the only one. Can you say that again?
Yeah. Absolutely. But it is rather arbitrary. This is why I told kind of the longitudinal story. Like, why did they set 0 degrees longitude at Greenwich Village? At Greenwich, not Greenwich Village, at Greenwich, England. It's like, well, that's where the Royal Observatory was. Right? It's a bit arbitrary, but they need a 0 point for it. Same thing turns out to be the case when you're setting up the sky's coordinate system as well. So when you look up out at the sky, you let me see if I have a better one. No, this one's fine. So you basically have the Earth's equator, right, which sets up the celestial equator, kind of extend it in all directions, right? You also have the ecliptic, which is the path of the sun in the sky. Now, if you look up at the sky, the sun follows an arc across the sky, right? Everybody's familiar with that. The planets also follow that same path because they're all in the same plane as the sun. Everybody's all in the same plane. So if you go out at night and you're looking for Mars and Jupiter and all those guys, where should you be looking? You should be looking at the same place where the sun went across the sky. That's called the ecliptic, right? Now, at some point, that ecliptic actually, at some point in the year, the arc where the sun is tracing out this path on a day-to-day basis is going to intersect with the actual celestial equator. It's during the spring equinox, right, where the planets actually, this is actually also when the equator is going to be getting the most sun, right, because it's right between the north and south hemispheres. Remember, when it's summer for us up here, it's winter down south. When it's winter down there, it's summer. So when the equator is kind of like getting the most amount of sun right at spring equinox, right? So when the sun is at that point, that equal point between, for the equator, is the place on the star map, that moment is the point where they ascribe the 0 point for the right ascension.
That actually makes more sense.
It's
because if the sun is passing through your vertical 0 point of the latitude, right? The equator, then right when it's already in the middle, might as well make that the middle of the other direction.
Yeah, it makes a little bit of sense. They could have said it really anywhere though. They just needed a standard point for it, right? At the end of the day.
Makes more sense in Greenwich.
Yeah. I guess they could have just said like the 0 point is going to be where the sun crosses Greenwich on Christmas or something if they wanted to. But anyways, so that's that. That's how we're dividing up the sky. I think that we don't need to belabor this point. Again, this is how star maps are written. Often you'll see the ecliptic kind of winding through, and you'll see how the sun traces its path out over the course of the year. This is the path of the sun over the course of the year. But I just want you guys to be aware of that, because if you ever do get into astronomy, even just get a telescope with any of these coordinate systems, this will need to make sense to you, and it is very bizarre. Okay, let's go back to time. So I kind of cracked this open. Longitude is important for time. We're not really doing a section here. Next semester we'll do more. We'll take relativity apart and give it its full luxury, and we'll probably circle back on time. Special relativity has a lot to do with time. But time, what is it? This is always really fun. I want to hear from you guys. What is time? Yeah.
The fourth non-spatial dimension.
Oh, mathematical answer. Yes, the fourth non-spatial dimension. Yes, it is an attribute which can be ascribed to any, let's say, frame in a story of a physical system, for sure. Yes, which is another word for a matrix, which is how people tend to think about it in mathematical physics. It is an attribute. It is the standard attribute which can be ascribed to any point in your system in a movie, basically. What else, though? What's it? Yeah.
The only answer I would like the angle put to that is just existence.
Existence. The unfolding of existence, perhaps. Yeah. What else? Brendan, is it? Yep.
I think of time as a way to measure how short or long things are.
Duration. Relative to each other, though, right?
Yeah.
There is something very relativistic about it. It's a comparison, right? Because when you can have an experience, right, that feels like it's taking forever. Like maybe you have a really boring class and you're just like, oh my God, you're watching the clock and you know the clock's moving at the same rate, but it feels like it's taking forever. You can also be having a great time, and then the hours just fly by. Yeah, in the back, yeah, Mac.
When I first saw Interstellar, I was talking about this with my sister. We literally paused the movie and had like an hour long debate about what time is, because there's this whole thing for black holes and like how it dilates time.
Absolutely.
Um,
And what did you conclude?
the answer I kind of can only is like time is kind of an incredibly personal thing.
Mm.
And like where if you are moving in a spaceship near the speed of light, it's going to be a lot different than us here on the ground on Earth. It's just kind of like a personal thing. And if you try to explain it outside of that, you kind of go crazy. That's like at least like my very
Yeah, no, we're heating up. This is getting interesting. So I do think
like non-scientific brain. That's like how I just have to explain it to myself. Because if I try to think it in like grander context, it's just like I just go crazy insane.
Well, I think that it's good to go insane about some of this stuff. I mean, there is some truth in the fact that that there's a very personal element to this. That's what I was trying to get at. If you're in a really boring situation, time seems to go really slow. And honestly, if you're having the best time of your time, it's hard to even say this without time. When you're having a great time, time flies by, right? This is actually one of the most miserable pieces of the whole deal of life. Is the better your life is going, the quicker it's over, which is really unfortunate. And then when things are not going well, it just drags on forever. So many hands up. This is awesome. Brandon, one more time.
I want to touch on your point one more time. There was a almost experiment. It's not quite the right word, but I think NASA did a little bit of experimentation with time.
Yes.
They sent one twin to the moon and one kept here on Earth.
Well, they didn't actually do that, but they had a clock that was doing an elliptical orbit around the Earth.
Yeah.
They actually had a satellite that broke. Is how this first happened.
And the one that made it into space had less time and was somewhat younger than the other twin.
Yeah.
Yes.
Yeah.
Oh, the twins.
Yeah.
That's so funny. I see. Did they put a clock on the guy or what? How did they measure his time?
Biological factors.
Oh, biological factors.
The age
Interesting. Did Mark Kelly go to the moon?
No, not the moon.
Okay.
Orbiting.
It's orbiting. Okay, I see. Well, yeah, so you can quantify this too, actually. So they've had this experiment too. It was barely an experiment. It was actually a comm satellite that got broken. It was supposed to be doing a geostationary orbit where it just sort of parks and orbits at the same speed as the Earth turns. And it broke and it started doing an elliptical orbit. And they noticed that actually as it drifted closer to Earth, that the clock changed. Actually, the clock slowed down when it got closer to Earth. Now, that seems super spooky. Who thinks that's spooky, at least? Do you guys think that's spooky? I thought it was really spooky at first, too, and then I started thinking about it really hard. And I have a tendency to destroy all spooky ideas when I think about them too hard, unfortunately.
Still looking for definitions.
No. Oh, for time? Let's come back to it. 1 second.
Sure.
Let's make sense of this time slowing business first. Yeah.
Oh, okay. Because I was gonna say that I think of time as two different things. Because there's the perception of time from an individual, which is relativistic.
That's what Max is getting at to some extent. Yeah.
But there's also time as in,
Measured.
yeah, even if it's not measured, but time is just the unassailable constant of the universe, the only one that's generally constant. Because no matter what you do, no matter how it changes or slows, it never stops. It always goes. It's always moving, marching along, no matter how fast or slow it goes. It's always moving.
It's always unfolding. Change is the only constant. I've heard that said. Einstein wrote that the speed of light is constant. There's some sort of constancy that people are always aiming to have as a background. Did you have a thought, Andrew? I want to come back to this this experiment before we move on, though. Yeah.
So I think what we're talking about what Dante said, and is it Max? Just a definition that I think might encapsulate some of this is that we're talking about a system of measuring our perception of the propagation of the universe from our frame of reference
Yeah.
at any given point.
Absolutely. Yeah. We're definitely trying to construct a system of measuring how things unfold, right?
The issue is that we don't, all of our understandings of our own frames of reference, talking about the time dilation,
Yeah.
is that we don't know how fast we're moving because there is no absolute frame of reference for the universe.
That's the really, really difficult piece of this puzzle. And this is, by the way, people prior to general relativity and special relativity, everybody was desperate to come up with a universal reference frame by which they could measure such things as time, right? There's something that's objectively on the outside which we can use as a clock, basically, or a distance, or a measuring tape.
As we approach the speed of light, our perception of time slows down, or our experience of time slows down. Right?
Perhaps that's one interpretation of the fact of some of these experiments and some of these relational attributes, which I want to unpack a little bit more.
We don't know how fast we're actually traveling. All of our frames.
Yeah, relative to what? Yeah.
Relative to what? Right. So we've got the actual velocity of the Earth's rotation, the Earth's revolution around the sun, solar systems traversal through the galaxy, our galaxy's traversal through the universe.
Yeah.
We don't know what other accumulated velocities we had.
Yeah, well,
right?
Yeah, I mean, you can start to add all of those up, but there's still nobody standing still at the end of the day.
Nobody's standing still. So if you could stand still,
Yeah.
how fast is the universe actually propagating? Are we just
What would it even mean to stand still?
just a little spark?
Yeah.
And,
Well, it brings up the question, like, what's a location?
right.
A location is just your distance to everything else around you. If you don't have anything around you, then you don't really have a location. If you don't have a location, you're not really part of the universe.
How do you know we're not just a little spark from a firework of the Big Bang that's blinked out at an instant? If our experience of time is dilated to the point where we're seeing things in from a very slowly propagating frame of reference.
Well, maybe so. I mean, we could pick on the Big Bang if we wanted to, but we'll save that for next semester. I want to take apart this gosh darn experiment about the clock slowing down in orbit, first of all. All right, so just want to throw a little bit of water on this a little bit.
Yeah.
All right, so your clock slows down. The problem is that in physics, up to the present, the only robust way that we can define the word time is what our clocks do. That's the only way that it's used in these equations, including general relativity and everything else. Time is what clocks do. So you might say, well, what the heck is a clock? And a clock really is just some sort of predictable motion that you can compare other motions to, right? So I got this thing, it's going around my clock over here, it's got hands, they're moving at a predictable speed, and I can compare other things happening in the classroom to that speed, that motion, which is very predictable, and I can gauge the rate at which things are unfolding in the classroom, right? Pretty simple idea. That's what clocks are. Seems like a solid idea. Now, what happens, this one's nice. It's a battery-powered clock and everything, quartz-based clock. So you give it some jolt and the quartz vibrates a little bit, and it vibrates at a particular frequency, so we can measure the second with that, which is really nice. So we can keep it kind of locked in to we're basically clocking it off of the vibration of the quartz. Okay, that's really nice. Let's think about let's come back to that one. So what about like a more primitive clock, like that pendulum, like we were talking about pendulums earlier. So anybody have like a grandmother clock, or are they really called grandma clocks, grandmother clocks? The pendulum clocks, you've seen these, right? Well, okay, pendulum clocks, also pretty good. As long as you keep them wound up, based on the gearing systems, I actually have no idea how the heck they work. I know they're very, very technically complex, but they have a very standard motion, which is quite predictable, which makes it a good clock under most circumstances. Now, what happens if I take that grandmother clock up into my satellite and I try to run this experiment? What happens? Well, time's gonna stop according to my grandma clock, right? It ain't gonna work. I can do the same thing with some other clocks too. How about if what happens if I take my grandma clock and I take it up on Mount Everest? What's gonna happen? It's gonna be different because there's less gravity on Mount Everest than there is down here. Now, is that because like the actual concept of time caused it to be different? Or is that because clocks react to their environments because they're tethered to atoms just like the rest of us? And when you are close to a big ball of atoms like the Earth, you are going to experience a lot more tension and pressure, which is going to restrict your motion than when you're up in space. So the clocks that were used for that satellite experiment are these atomic clocks. The way that they measure is very similar to the quartz clock. There's some sort of element in there, I think it's a cesium, that has a predictable vibration rate to it. So the light that it emits tells you by its frequency the vibration rate of this cesium atom, which is being electrically stimulated, just like the quartz clock, but slightly different optical readout. That cesium atom, we could do this with our quartz clock too. If I take it down on Earth and I have a cesium atom and it's vibrating, do you think it's going to have an easier time or a harder time vibrating when it's around a bunch of other atoms? It's like, well, everything we know about the concept of mass, which we already talked about, is just a complete rabbit hole. But the least we can say is that mass seems to scale how connected you are to the people around you, the atoms around you, to some extent. Larger objects have more atoms, they're more connected to the atoms when they're next to them. They have more connectivity, they have more tension, they have more pull. The same thing is going to be true of the atom in that cesium atomic clock. It's also going to be more connected to other atoms when it's close by to other atoms. That's just by virtue of its geometry. So it might not, my point is like, it might not be completely nuts. I mean, it's perhaps as nuts as gravity itself, but it might not be completely nuts that clocks slow down or speed up depending on whether they're around lots of atoms or not. You guys see what my point here? So, I tend to think of that as having some sort of answer that's lodged inside of the bigger question about what the heck is mass and gravity, and from an architectural standpoint, what causes an atom to experience more or less mass? Why do the ones with bigger numbers have more mass? There's probably a solution that would also explain why those atoms experience more or less vibration when they are close to large bodies, large groups of atoms to begin with. It doesn't have to be the concept of time that's warping so much as what's happening to the clocks themselves. Yeah. Which might affect you if you're an astronaut too. Maybe your cells actually are under less pressure and more pressure, and it actually changes your actual physical body. Why not?
I remember I was reading an article about that experiment, and there's an addendum that they had tried the same thing with a digital clock. It didn't change.
Interesting. Wonder.
Digital clock change, like any change that was there was so. It was
Yeah, they're not as precise. Yeah, they're very, very small changes, by the way.
matter
Yeah.
comparatively to their previous experiment, because what they found was it was just the physical mechanics of the clock change.
Yeah.
Its physical experience.
Made out of atoms, man. Yeah, it's horrible. So I guess this my caution too with all of this is that time is a really difficult concept to generalize. Not only because, like Andrew pointed out, we don't have a universal background, we have no universal motion to compare it to, but we're really relegated to the environment under which our clocks are standardized. This clock works great right here. But yeah, if I take it on a spaceship going a gazillion, accelerating at gazillion miles per hour, or I take it, up into space, it might behave differently. And that might not be spooky. That might just be a product of our kind of infantile conception of how gravity works on a mechanical basis. Which is fine. There's lots of work to do. I love it. So, all right. Yes, Ezra.
I just want to make sure I understand entirely what you're saying. So you're saying that instead of time kind of changing depending on how the gravity is, the objects are changing depending on velocity or their environment.
Yeah, that's basically right. My point is also, this kind of circles back on, and I'm gonna keep circling back on this, especially, yeah. If you guys stick with me, this is the reason that I'm really insistent on making sure that when we talk about physical explanations for phenomena, that the physical explanations have physical actors that are acting out the explanation. Time's a concept. It's a comparison of two motions, or it's motion with memory of some sort. It's a concept. It's a relational idea, right? Bodies, material objects, they're not relational at all. They're just defined by their architecture. And so what's happening is that we have a mechanical material device that we use to assess this relational concept of time. In other words, we create a periodic motion that we can measure, that we can compare other motions to it. That's our clock. And then when our clock, made out of atoms, behaves strangely, or not even strangely, but seems to respond to gravitational pressure, we go, wow, that's totally supernatural and weird. It's like time itself was warped, right? It's like, well, since you defined time as what clocks do, then yeah, your clock's behavior did get warped, but maybe that has more to do with what's happening to the atoms in your clock. So, because, what's the alternative? The alternative is that you apply physical processes to ideas, which is poetic, it's beautiful, the time was warped. It's like, it is beautiful, and I think it recaptures something that happens in our lives. That's why I liked Max's point about it being personal to some extent, and that's why I said, like, it's actually kind of a very melancholy tragedy to this, because time really does go fast when everything's going good for you, and that's really sad, because then your life is over. But there's something very personal about the way we experience time. But for physics, it's really just a comparison of some standardized motion, and the best we can do is clocks, unfortunately, for better or for worse. So I think there's different levels of profundity to all of this, and the physics side might be the least profound. Yeah.
One thing I often think of with time is, it's why I brought up at first, it's the fourth non-spatial dimension, is because when you think of, say you want to meet someone somewhere,
Yeah.
you can have the exact coordinates of where you want to be, but if you don't have the same time, you're not going to see each other.
Yeah, it's true. It's a good coordinate to have.
But it doesn't matter.
Yeah.
Because if you're not there at the exact same time,
Yeah.
you're not going to. It's just not.
It's super important, super useful.
And so they're intrinsically connected.
Yeah. Yeah. Yeah, I mean, and that's why it was, I didn't even really get into this, but it was an insane quest to figure out how to build reliable clocks back in the sort of imperial maritime navigation period, right? We've talked about how England had the biggest navy in the world. I guarantee you they had the best clocks in the world too. And that was that was just, hundreds of years of people iterating on clock designs, trying to dial it in, because exactly right. You have to know that piece of the puzzle in order to actually orient yourself to anything. You need to be at class on time. If you come here like at 6 o'clock, no one's going to be here. And, that would be a waste of everybody's time. So it is really interesting. Yeah, and people proposed insane ideas. Galileo actually proposed a clock system. There's a big contest, and I believe he proposed one that was based on the phases of Jupiter's moons, because, his big discovery was, oh, wow, Jupiter has moons going around it. And he was like, I can actually work out the time that it takes for Jupiter's moons to go around. And so if you use my device, he concocted this elaborate device you put on your head or something. You could see the phases of Jupiter's moons and reference some hand manual, or I don't know, some dials on it or something, and basically calculate what time of day it was on Earth, or how much time had passed since the last time you hooked it up or something. People had wild ideas about how to keep time, because they were looking for that precision, and the precision's really hard to get with something like looking at the sun, looking at the moon. It's just not as reliable. Yeah.
That's just the sequence of events. Basically, everyone's gonna everyone gets born, but inevitably everybody dies. So even if it's a precious time,
Did you say everybody gets born, but not everybody dies?
no, no, inevitably, everybody dies. Everybody.
Oh.
So, I get time to be precious too, but it's each person gonna have their own each person's gonna have the they think it's precious about their time and other people.
Yeah. Yeah. Yeah, there's two sides of it, right? There's an experiential, personal side to it, and then there's the thing that clocks do, right? And they're very, very different. I think if you guys start paying attention to this, you'll notice, there's what that thing is doing is not necessarily what's happening inside of you, and it's a very, very different experience.
That's what I call it, the perception of time.
The perception of time, yeah.
I remember I've seen a video about this, and I'll probably somewhat butcher exactly how it goes, but it's I think it's an ancient African way of viewing time, and their perception is time only only exists when you create a moment. So it's if you're just sitting there doing nothing, there's no time is really nothing's really happening.
Like events.
Yeah, so there's no an event is what's creating that time. So there's no real concept of the future with that system, because it's because you don't know what necessarily is going to be happening next, and you can't that time can't you can't even perceive that time yet because the event hasn't happened. So it just doesn't exist basically. I don't know.
There's been a lot of So time feeds into cosmologies too. We'll do this more next semester. But yeah, different cultures have set up different ways of thinking about these. The rhythms, a lot of cultures have a very cyclic cosmology where things will happen again. Yeah, it's you get into some really interesting arguments, even from a Western scientific standpoint. Before the Big Bang became popular in the 1970s, most scientists embraced a kind of eternal universe of some sort. They kind of didn't think there was a beginning or an end, because they were mostly rebelling against the church that said that there was a beginning and there will be an end. They were like, no, there isn't. We have no reason to believe that. So, that justifies interesting cosmologies, because if there is no beginning or end to time, then one could make the argument, in fact, Nietzsche famously made this argument, that eventually the universe, will run out of possibilities and it'll start repeating itself. Which, think about that sometime. I'm not sure I agree with him about that, but it's an interesting argument. And so his point was that you're going to eventually have to relive your life all over again. It's going to be gazillions of years in the future, but given eternity, this will all happen all over again, and maybe you can change one little thing or something. But it turns out that a lot of cultures have a very similar cosmology. The Indian cosmology in ancient India, all the way up to the Hindu tradition, to some extent, has a very cyclic cosmology about reliving. There's this idea of rebirth, and what's that movie? You guys ever see The Fountain? That movie? No.
With the John Krasinski and
Yeah, it's a Darren Aronofsky movie. It's really good. It's one of my favorite movies. I mean, it's a little over the top. It's pretty over the top, but I love it. because it kind of has this cyclic cosmology where these, like, there's a couple in it, they've lived in multiple different lifetimes together. Again, this is all just, it's all really how any particular individual relates to time, how cultures relate to time. And in some sense, a lot of these can be mapped rationally onto the way that the Western scientific paradigm views time. Of course, we're locked into this Big Bang universe at the moment, but I think that's a little more of a modern trend than something that will necessarily stand the test of time. Yeah.
Clarify, like earlier we were talking about like there being like a fiery and everything. Like we mean everything, right? Not just like us in our solar system.
Yeah, yeah. I don't put much faith in it personally. But yeah, that's the Big Bang cosmology. It ends in the heat death of everything, basically. So
So instead of like everything dies of explosion, it's just all the stars die out and everything's cold.
yeah, and just dissipates, and yeah, it's I don't know. In some sense, I think that those kind of, gosh, you guys are just, there's no way to not talk about cosmologies. It's just so overarching. In some sense, I wonder how much that just reflects people's sort of ennui or nihilism about modernity or something like that. I think we have a tendency to ascribe these grand cosmic stories to reflect how we view the fate of our own civilization in some sense. I don't think we're locked in any particular fate, despite how good or bad people perceive things to be going at the moment. But I think that the Big Bang cosmology kind of, it really has a very apocalyptic vibe to it, and that can be popular in times of stress for a civilization. We've seen lots of apocalyptic cosmologies come and go over the years. Yeah.
There's one more theory that I'm remembering slightly because there's the multiversal theory that's sort of popular now as well. And I want to say that the conception of time from that perspective is the resolution at which, or sorry, the interval at which the universe
branches. Yeah.
These sort of quantum possibilities.
Yeah. So you could kind of define that by time as kind of the ticking upon which the movies of the universal movie play out. Basically, if it was kind of like a film with individual frames. But at the end of the day, you're just kind of finding a way to chop things up so you can handle them. I think a lot of these, especially these mathematical physicists, really want to find ways to grid everything out so they can make better, tighter simulations and predictions, and I don't fault them for that. I'm not sure how much it reflects about actual reality as much as about their goals with trying to formulate predictions about how their systems are going to unfold and stuff like that. I think we'll get better and better at clocks. I think we might, it's conceivable to me we could develop one that wasn't as affected by gravity, and we might get very different results as a consequence of that. But yeah, time is just it is both deeply metaphysically profound and important to our daily lives and our experiences, and it's really important to the measurements of everything we do in astronomy too, right? Because what do we say all the time? We say that star system is 4 light years away. We're talking about distance as a measured in time of travel, right? Because we assume light goes at the same speed, which maybe has some caveats, some asterisks on it as well. But this is really, really important to how we gauge things. And so we have this measurement side of time as well, and we can get fooled by it. So I don't know. This is one of my favorite topics. We can keep coming back to this as the course unfolds. By the way, I guess this might be a good moment for me to introduce your final project a little bit. So you guys are doing these short little videos every week. In some sense, that's to get you prepared. Right now, they've been pretty simple. I haven't really made you analyze. Oh, you guys analyzed the video a little bit, or I think you summarized the video last week. But you're going to get a little bit more analytic as the weeks wear on. And what I'm ultimately going to have you build towards is really comparing some sort of phenomenon or a body in the solar system. We're going to be talking about different bodies, planets and asteroids, but we're also talking about concepts like time. And what I really want you guys to do for your final project is to make a much longer video. Not much longer, but I want you to go in depth, and I want you to analyze with a few different decent sources from the scientific literature to compare 2 different perspectives on some origin story for one of these planets or some concept, like time if it interests you, something like that. So you can start kind of chewing on ideas as they come up in class in the back of your head. Well, this is something I really find interesting. Maybe I can find a few different theories about this and compare and contrast them. Again, you guys are in college not just to get a piece of paper, but you got to learn how to compare ideas that are often in conflict with each other, because that's what real life is all about. Sorting out bad ideas that look tasty from the good ones that look gross. Sometimes the best ideas don't look tasty. What's that? What's that? What's that?
For a second, I thought you said life was about conflict.
Well, it kind of is. It's about conflict and tension and resolution. And yeah, I mean, just being a being in the world, I think, is all about navigating conflict, navigating conflicting information, conflicting theories. Like, this is the hardest part of being alive in some sense, is trying to figure that out. It could be in your personal life with your relationships, but it could also just be in terms of understanding how the world works, who's trying to get your money, who wants your vote, why they want it, who they are, what they're all about. Yeah.
Just verifying, did you say the final project is gonna be a video?
It's a video. It's a video presentation, yeah. You can work with a partner, too, if you want. You guys all seem to not really know each other, though, prior to this class, so maybe. But if you want to work with a partner, you're welcome to. Just do twice as much work. I'll put up a rubric for that soon enough. I just wanted to get you guys sort of thinking about it in the back of your head. You know, there's going to be a subject or a planet or a process or something that's going to come up, and I want you guys to essentially research it and go deep and compare, because I think what most people have no idea about on the outside of the scientific world, and in some sense this is a generalized science class. We get to use the solar system to talk about how science works, but it's more about how science works. The specifics are pretty cool too, but my point is I think most people on the street have no idea that there's insane, bloody arguments going on beneath the surface about all of these ideas all the time. There always have been. There are right now. So when you see somebody, you know, in some government organization being like, this is how the science works on this thing, it's like there's an enormous argument going on beneath the surface with whatever, you know, given perspective is being talked about. Your textbook, every single thing that it's like, well, we figured this out, we figured that out. It's like, there's these huge dramas going on, and they're going on right now, and you can find out about them. And that's kind of what I want you guys to do for this final project, basically. I want you to see what's actually happening. Yeah.
Assuming we'll be able to break, but I want to ask, like, so I can get started a little bit.
Yeah.
Do you want to stay inside the solar system, or can we go to like?
I would prefer it, yeah. At least something we've talked about in class. Because next semester you'll do it with something more celestial. Yeah.
Can I do it with a theoretical body, like Planet 10?
Yes. Yeah, you can do that. We'll talk about Planet 10. Yeah. But yeah, you have to be able to find two pretty interesting perspectives on it is the trick. So I don't know if you can do that. I know a guy who worked on that. He's still working on that down at Caltech. It's actually like a vibrant field of inquiry, but I don't know that there's like multiple conflicting opinions about it. Maybe there are. There is for everything. What am I talking about? I just got done telling you guys there's always. Yeah, but it's gonna probably be a little more nuanced. Somebody's gonna say, well, it did, or it did, or it doesn't, and here's why it looks like it does.
Because we got the math for Uranus wrong.
Whatever it is, yeah. I want you guys to find some sort of interesting subterranean debate about something that seems like it's all settled and nailed down. I saw a really interesting paper this morning. We'll get to this again, but I think it's come up before already. And it was just one of those pop science. I just sometimes look at like the news feed or whatever on Google, and I saw this, and mine's like mostly science and electric guitars and stuff. But I looked at this one article, and it was like, should we be calling the icy giants rocky giants instead? I was like, ooh, that's really interesting. And it's referencing this paper that just came out. It's like barely even published. It's on Archive, which is kind of the preprint server for physics papers. And the guys, you know, it's a sensational headline, but they're arguing something which is really interesting, which I think I've pointed out already in this class, and we'll get back to it, which is that, you know, the thing that's under our feet, this really dense rocky planet, there's two more of these in the solar system. They're inside of they're inside of Neptune and Uranus, the big ice giants. And so they're making this kind of formalizing this argument in some sense. So that was really interesting. There's just all these little pieces, and you're not going to really hear about that until it makes the textbooks, I guess is what it's going to come down to. But I think it will be super good for you guys to find one of these little subterranean arguments in the underground, in the scientific underground where nobody goes. People just want to see the textbooks and the headlines for the most part. And there's cool stuff happening. So
Just want to see the science TikToks.
the science TikToks, yeah. Well, subscribe to ours while you're at it. I'm just kidding. Okay.
Haven't already.
Yeah, if you haven't already. We got 5 minutes left. I'm gonna let's see, what part of this story can I fit into 5 minutes? There's there's kind of one little interesting story. I'll tell you this story before you go. The length of the day. How long is the day?
A little over 23 hours.
It depends how you measure it, is the answer to the question. This is what's really kind of fun. So there's two ways to measure this, right? So you can measure how long it takes for the Earth to rotate around and come back to a fixed star, right? That's a legitimate it's a rotation of the Earth, which is what a day is, right? Or you can measure how long it takes to come back to the sunrise, right? From sunrise to sunrise. The crazy thing is that since the Earth is moving, you actually will find yourself coming back to the sun at a different time than you will if you're measuring to a fixed star. So this was actually quite interesting in the history. So like the time required for that extra rotation to go and face the sun, since the Earth is turning this way, it's got to turn a little bit backwards to face the sun. It's a really small amount. I think it's 1/365th of a full turn, right? Because that's a year, and you're making your way around. But it comes out to like 4 minutes, right? So you said 23 hours and change, basically, which is it's accurate for the mean solar day. However, it's not correct with respect to stars. And there's an interesting little story to tell, which is that there was this guy who was working on radio satellites back in the 1930s, this guy named Jansky. And he noticed that there was this really weird hiss on his satellite dish that he was tuning over at Bell Labs somewhere. And it showed up a few minutes before sunrise every day. And he was like, what the heck is that? And through, I think he went away, thought about this for a long time, and he realized that it must be coming from somewhere other than the solar system. It must be coming from the stars somewhere. And it turned out that he was able to map this hiss onto the center of the Milky Way galaxy, actually. And this turned out to be really, really cool because all of a sudden you could use radios, right? People were just using them for communication and tracking bombers and stuff like that. But all of a sudden you could point it at the stars and get information about a kind of light, radio waves, coming from the stars for the first time. And so people began to actually use that as an almost color in which they could paint different structures in the sky. So that was really a product of realizing that there was a difference between where the stars line up 4 minutes before the sun comes up. That's a really, really interesting, another one of those just kind of like brilliant little insights. Like, wait a second, this is a sidereal day when this phenomenon is happening again. I think we must be looking at something in the stars. I think there's a radio source coming from the stars. And now radio telescopes are some of the most popular and far-reaching, deep penetrating telescopes that we have. So that's pretty cool. What's that?
That makes sense. They're slow.
They're slow. They're big. Yeah, you can set up some baselines. We'll talk about telescopes a little bit going forward. Let's see where we're going to go from here really quick, just so I can preview it before I let you go. We're going to end up talking a little bit about how we need to talk a bit about seasons. We introduced them. We're also going to talk a little bit about the difference between climate and weather, which is really fun always. And then I think we'll get onto actual telescopes and light, and eventually, don't worry, we will talk about the solar system. So I will not say have a good weekend because it's only Tuesday, so I'll see you guys on Thursday, and have a good weak, I guess. We'll leave it at that.